In this session, we're going to see augmented matrices, and we're going to see how they can be used to solve systems of equations. To get started, let's go ahead and remember how we would solve a system by elimination. We'll start with the system 3x minus 6y equals 9, 2x plus y equals negative 4. What I'm going to do is multiply the first equation by 2, and then the second equation by negative 3. Let me be a little bit more careful here. We're going to multiply both sides of the first and both sides of the second. And in so doing, we're going to eliminate the x's. So multiplying the first equation by 2 gives me 6x minus 12y equals 18. The second equation by negative 3 gives me negative 6x minus 3y equals 12. Adding those together gives me negative 15y equals 30. Before I go ahead and solve this, what I want to do is I want to set this up in a slightly different structure than we've seen before. So I'm going to rewrite the system, replacing the second equation with this one we just came up with. So our system now becomes 3x minus 6y equals 9, and then negative 15y equals 30. Dividing both sides of the second equation by negative 15 is going to give me that y is negative 2. Might as well go ahead and do that. Let me rewrite what we have. And now we have this new system, 3x minus 6y equals 9, and y equals negative 2. Now I want to eliminate the y's, and so I'm going to multiply both sides of the second equation by 6, and then add the equations together. And when I do that, I get 3x equals negative 3. I'm going to replace the first equation by that one. And our system, which is starting to become very uninteresting, is 3x equals negative 3, y equals negative 2. And of course, I can go ahead and say then that x must equal negative 1 by dividing by 3, and y is equal to negative 2. And it's hard to think of that as a system. What we would say at this point is that xy is equal to negative 1, negative 2, and none of this was new. I just want to connect things we've known with new things. And in this case, the new thing is going to be a matrix. A matrix is a rectangular array of numbers enclosed by square brackets. The original system that we just solved, we're going to now solve it using matrices, and what I want to emphasize and highlight is that all the steps are the same. We're just representing the situations visually in a slightly different way. Our original system, 3x minus 6y equals 9, 2x plus y equals negative 4. Oh yeah, you may have noticed the first equation could have been divided through by 3. We could have done that, didn't think of it at the time. Now that I've thought of it, I still don't want to do it because I want these steps to look identical to what we just did. Although, right off the bat, you can do that. Okay, now that that's out of the way, let's write this down as an augmented matrix. We're going to use square bracket because that's a requirement for matrices. And I'm going to write down just the numbers, 3, negative 6, 9. Those are the numbers that exist in the first equation. The second equation has the numbers 2, the coefficient of y, since it's not there, is 1, and then negative 4. This is a matrix. It's numbers. They're rectangularly arranged. Square brackets. The augmented part, if you're referring to the word that I just used a minute ago, is a vertical line that separates the part that refers to the coefficients of the variables from the numbers that are on the right-hand side of the equal sign. Essentially, we could think of the first column as being the coefficients of x, the second column as being the coefficients on y, the third column as the constants, and the vertical line is the equals, or it's where the equals goes. So in order to put a system of equations into an augmented matrix, it should be in standard form, where the x's line up, the y's line up, we have our equals lining up, and then our constants line up, all in the same columns. Now, since these rows of the augmented matrix represent equations of the system, what we can do is add rows together, multiplying where appropriate, eliminate entries, and replace rows by the result of that. Those are called row operations. Informally, and I cannot stress that enough, informally, row operations are things we do to rows that are like what we do to equations. All right, let me get rid of that, make some room, and we're going to get to work on this augmented matrix. Okay, so I'm going to rewrite the augmented matrix because I've already written all over the other one. So we have 3, -6, 9, and 2, 1, -4. And as you'll find as we go through this, all these videos on matrices, I refer to the numbers, I say them in the rows, not the columns, in the rows. Okay, what we want is we want a 0 in the lower left corner, and we want a 0 in the upper right corner. I'll show you why that's true in a minute, but right now that's just what we want. I'm going to start with the lower left corner. And since what we're about to do is like what we've done to equations, what I want to do is I'm going to note, we're going to replace the second row, so r sub 2, and a little arrow indicating we're going to replace it by 2 times row 1 minus 3 times row 2. This is just shorthand for what we've already done. In other words, when I write down 6, -12, 18, and then -6, -3, 12, I'm writing down the result of multiplying equations by numbers, except I don't have to write down the pluses or the variables or the equal signs. 6 minus 6 is 0, -12 minus 3 is -15, and then 18 plus 12 is 30. Now this represents an equation. The equation that it represents is -15y is equal to 30. Since I could divide both sides of an equation by a number, I can divide a row in an augmented matrix by a number. In this case, it's going to be -15. Dividing that equation by -15 is like dividing that resulting row by -15. And so I'm going to go ahead and denote where we write down I'm replacing row 2 by the result of what we just did, divided by -15. This new row becomes 0, 1, -2, and that's what I'm going to end up replacing the second row by. And now I have this new augmented matrix, 3, -6, 9, 0, 1, -2, that should resemble a lot one of the systems that we wrote down a few minutes ago when we were eliminating variables. As a matter of fact, the second row of this, 0, 1, -2, represents an equation. It represents that 1y is equal to -2. Not a shock, we already knew that was true. Well, I'm not done yet. Yeah, we could pull it out of the matrix at this point because the first row represents an equation. We can figure out what x is, but I want to bring this all the way home. I want to go ahead and get a 0 in the upper right where the -6 is. So let me erase the equation we just wrote down. And what I want to do is I actually want to replace row 1 by doing something that will get rid of that -6. In other words, I want row 1 to be replaced by row 1 plus 6 times row 2. Row 1 is 3, -6, 9. 6 times row 2 is 0, 6, -12. When I add those together, I get 3, 0, -3. And since everything is divisible by 3 and this represents an equation, what I want to do is divide the row by 3. And I get 1, 0, -1. This is going to replace the first row. So when I rewrite my augmented matrix now, I've got 1, 0, -1, and then 0, 1, -2. This was an augmented matrix before, it's still an augmented matrix now. When you're writing these, don't neglect the brackets. It's a math thing, but if the brackets were a different symbol, this would actually have a different meaning. And so I need to know that you know that the brackets are required. The first row, 1, 0, negative 1, corresponds to an equation. 1x plus 0y equals negative 1. So x equals negative 1. The second row, 0, 1, negative 2, also corresponds to an equation. 0x plus y equals negative 2. In the context of a system of equations, what we would then say is xy is equal to negative 1, negative 2. The exact same thing we came up with a minute ago, but we did it using this different technique of an augmented matrix. If you compare side by side the steps that we took to eliminate the x and then y from the original system of equations using equations, with the matrices that we wrote down, you're going to see that the same numbers are showing up. We aren't doing anything new, we're just representing it visually in a different way. Okay, so now we're going to solve a system using an augmented matrix. Those instructions are the ones you might see. You might also see using Gaussian elimination, which is essentially the process of turning the left part of the augmented matrix into something with ones and zeros. Since that's what I'm going to keep showing you, I don't think I need to stress the vocabulary, but this is using an augmented matrix, and I suppose I should say look for either augmented matrix or Gaussian elimination in instructions on an exam to let you know you should use the technique we're about to use. First, I'm going to write down the system, which is 3x minus 4y equals 12 and 8y minus 6x equals 9 into standard form with the x's in the same columns. I don't know if you caught that. They're not. So now we have 3x minus 4y equals 12 and negative 6x plus 8y equals 9. That is going to go into an augmented matrix. 3, negative 4, 12, negative 6, 8, 9, a vertical line where the equal signs go, and then square brackets to actually end up with a matrix. Now our pattern is going to be, I want a 0 in the lower left and a 0 in the upper right of the left portion of the augmented matrix. I want to start with the one in the lower left. You're going to see me do this just about every time. And I'm also going to note what we're going to do. We are going to replace row 2 by, what would I need to multiply the first one or the second one by, so that when I add the two columns together, I get a 0. The answer is 2 times row 1 would do it. Add that to row 2. Don't be a hero. Write down what happens when you multiply row 1 by 2. So in this case, we have 6, negative 8, 24. And then negative 6, 8, 9. And this gives me a 0, a 0, and a 33. Well, we can put that into the matrix. And so we have 3, negative 4, 12. And then 0, 0, 33. But as a matter of fact, this second row indicates that 0x plus 0y is equal to 33. This is a false statement, also known as a contradiction. For those of you into the vocabulary, that means this is an inconsistent system, which has no solution. So I'll write the empty set symbol, the zero looking thing with a slash through it. That's it. So that's how you recognize an inconsistent system. Zeros on the left in an augmented matrix, and then non-zero number on the right, which indicates an equation that can't be true. No solution. Next, the system we're going to solve using an augmented matrix is x minus y plus 3z equals 4, x plus 2y minus 2z equals 10, and 3x minus y plus 5z equals 14. I want you to pause the video and write the augmented matrix that represents this system. I've got 1, negative 1, 3, 4, 1, 2, negative 2, 10, 3, negative 1, 5, 14, with that vertical line before the last column. Now, it's easy to lose track of what we're doing if we don't go about our business in a systematic way. Ultimately, what we want to have is zeros in this first column of the second row, the first column of the third row, and the second column of the third row. We also want zeros in the third column of the second row, the third column of the first row, and the second column of the first row. In other words, in this lower triangular area of the left part of the augmented thing, we want zeros. And in the upper right triangular area, we want zeros. Furthermore, we eventually want ones down the diagonal. That's what we call that, the diagonal of the matrix. When I have zeros in the left lower corner and zeros in the upper right corner and ones down the diagonal, then everything will be beautiful. That's the Gaussian thing that we are talking about a minute ago. Now, if we're not careful, when we find when we get our zero, we may lose it. So we have to be systematic about our business. I would recommend you go for zeros in the first entries of the second and third row. Do that first. Then go for a zero in the middle bottom, second. Then the third entries in the first two rows, do those third. And then the top middle, do that fourth. Basically, work our way counterclockwise, getting zeros in those strategic places. You don't have to do it this way, but I highly, highly recommend. It's been years of teaching for me to come up with this nice little, essentially 4-step systematic technique. Okay, so how do I get my first zero? Looks to me like if I replace row 2 by row 1 minus row 2, I'm going to end up with a 0 in that first entry of the second row. And then if I replace row 3 by, say, 3 times row 1 minus row 3, I'm going to have a 0 where that 3 is. I want you to go ahead and perform those two operations. And as I said, don't be a hero. Write down the rows to do the arithmetic and then bring it back to the matrix. Pause the video and do that. Okay, so after doing that, the first row hasn't changed. 1, negative 1, 3, 4. The second row became 0, negative 3, 5, negative 6. Remember, we did row 1 minus row 2. And then for 3 row 1 minus row 3, everything turned out to be even. I had 0, negative 2, 4, negative 2. So I divided that by negative 2. And the third row of my augmented matrix is now 0, 1, negative 2, 1. We have taken care of putting zeros in the first two places that we want them. Now what I want is a 0 in the middle of the bottom row. And here's where, if we're not careful, we can end up taking steps backwards. We worked really hard to get the 0 in the first entry of the last row. If I used the first row, which is 0, negative 1, 3, 4, the negative 1 from the first row and the 1 from the third row would add together and give me a 0. Yay! Except the 1 in the first position and the 0 would add together and give me 1. Boo! I'd lose the 0 that I worked so hard to get. So what I now want to do, so that I don't lose the 0, but I get the one that I want, is I want to use the second row. That's why we wanted the 2 zeros where we wanted them to begin with. So what I now want to do is I want to replace the third row by row 2 plus 3 times row 3. When I do that, I'm going to end up with a 0 in the middle of the third row like I want, without losing the 0 in the first entry of the third row. So go ahead and perform this operation and then come back to the video. Okay, so now I end up with my new augmented matrix. 1, negative 1, 3, 4, 0, negative 3, 5, negative 6, and 0, 0, negative 1, negative 3. I could multiply that bottom row by a negative 1, but right now having the negative works to my advantage. But know that you can do that. Now, if you wrote down, and I hope you did, what we want to do, we now want to get zeros in the third columns of the second and third rows. We're going to use row 3 to do that. That way we keep everything nice and tidy. So we're going to replace row 1 and we're going to replace row 2. Right? We're going to do 2 separate sets of row operations. I want you to figure out what we need to replace row 1 by and figure out what we need to replace row 2 by. Hint, for row 1 you're going to use rows 1 and 3. For row 2 you're going to use rows 2 and 3. Go ahead and do that and then come back to the video. So my first row has now been replaced by 1, -1, 0, -5. My second row, 0, -3, 0, -21. And my third row stayed the same, 0, 0, -1, -3. We can divide to get rid of the negatives and cut everything down to size. I will do that at the end. What I want to focus on now is we have one more place where we want a 0. It is the second entry of the top row, the second entry of the first row. And there's only one option to use, and that's the second and first rows. And in fact, what we're going to do is we're going to replace row 1 by, I don't know, let's say -3 times row 1 plus row 2. That would do it. Go ahead and do that. And then go ahead and do what you need to get 1s down the diagonal. You're going to divide by an appropriate number. And then come back when you have the resulting matrix. Okay, so I've stopped at an intermediate step here. My matrix is -3, 0, 0, -6, 0, -3, 0, -21, and 0, 0, -1, -3. If it wasn't clear before, now what I want to do is replace row 1 by row 1 divided by -3. I want to replace row 2 by also row 2 divided by -3. And then I want to replace row 3 by row 3 times -1. When I do that, I end up with 1, 0, 0, 2, 0, 1, 0, 7, and then 0, 0, 1, 3. Now remember that the first column corresponded to the variable x, the second the variable y, and the third the variable z. So the row 1, 0, 0, 2 represents the equation x equals 2. 0, 1, 0, 7 represents the equation y equals 7. And 0, 0, 1, 3 represents the equation z is equal to 3. In other words, the solution to our system, and I want you to give it to me as an ordered triple, x, y, z is equal to 273, which is readily readable from the augmented matrix, provided you know what it means. Now, just a little chat here. The zeros in the lower left triangle, they're essential, absolutely essential. The 1 in the third entry of the first row is what indicates to me that the value of z is 3. At that point, once you have that, you could, practically speaking, have jumped out of working with matrices a while back, as soon as we knew what z was, and you could have written down the second, whatever was in the second row and come up with a value for y. You could have then written down what was in the first row together with your value of y and z, and you could have solved the system using back substitution a few steps ago. But I don't want you to do that. I want you to bring it all the way home. I want you to get the zeros in the triangles and then the 1s down the diagonal. It's kind of an optional thing to get that far now. In a future section, it's going to be required. We might as well develop the practice with it now. That's one thing. Second thing, I don't care who you talk to. Wait till the end before you make that diagonal the 1s. Don't go dividing things unless you're going to end up with whole numbers. If you're about to divide a row so that you can get ones, and you're going to end up with fractions somewhere, stop it. Don't do it. Wait till the end. I don't care who tells you what. Do what I said. Last example for this session here. Solve the system. Give the complete solution. Our system is x plus 4y minus 2z equals negative 3, 2x minus y plus 5z equals 12, and 8x plus 5y plus 11z is equal to 30. I want you to pause the video and write down the augmented matrix. 1, 4, negative 2, negative 3, 2, negative 1, 5, 12, 8, 5, 11, 30. Now, just like we did before, I want you to get zeros in the first columns of the second and third rows. Pause it, do that, come back. Just to make sure we're on the right track, I'm going to replace row 2 by 2 times row 1 minus row 2, and then I'm going to replace row 3 by 4 times row 2 minus row 3. I want to note that when I reference rows 1, 2, and 3 right now, I'm referring to the rows as they currently exist in our augmented matrix. Just want to make sure that's clear. If you need to do your work some more, come back to the video. Otherwise, just keep watching. And here I get 1, 4, negative 2, negative 3, 0, 1, negative 1, negative 2, and then 0, 1, negative 1, negative 2. You notice I cut everything down to size, divided the second row by 9, the third row by negative 9, because, you know, I could. I got the same row twice. Let's mindlessly continue what we do, and I want to go ahead and get a 0 in the second entry of the third row. I'm going to do so by replacing row 3 by row 2 minus row 3. And when I do that, I get a matrix that has a row of zeros at the bottom. What does that last row, 0, 0, 0, 0, mean? Well, it's an equation. What equation is it? 0 equals 0. That's a true statement. That's an identity. That's a dependent system. Oh man, I like contradictions a lot better because then I can just say no solution. For the dependent system, now what I have to do is I have to take one of the rows, preferably one with a 0, and write down the equation that it represents. I'm going to do so with the second row. 0, 1, negative 2 represents the equation y minus z is equal to negative 2. What we're going to do is we're going to take this equation and solve it for a variable. Folks, go for the path of least resistance. If y minus z equals negative 2, then I'm going to add z and get y equals z minus 2. This is y in terms of z. Do you know where we're going next? I want x in terms of z. I'm going to do so by writing down the equation represented by the first row. Guess what? Since we didn't change it, that's the first equation we had in the system anyway. It is x plus 4y minus 2z is equal to negative 3. Since we have y in terms of z, we want x in terms of z. So I'm going to take this expression we have for y and substitute it in place of y in the equation we just wrote down. And so we have x plus 4 times the expression for y, which is z minus 2, minus 2z is equal to negative 3. I want you to go ahead and solve this equation for x. Pause the video and do that. After simplifying, I get x equals negative 2z plus 5. X is negative 2z plus 5. Y is z minus 2. We're going to write that down in a set notation. The set of x, y, z, such that x is equal to negative 2z plus 5. Y is equal to z minus 2, and z is any real number. That's what's meant by write the complete solution. I recognize to do that when I have a row of zeros, because 0 is equal to 0 is a true statement, which means I must do something like this. If I had, say, 0 is equal to 4, right, 0, 0, 0, 4, then we'd say it's no solution, and that's the difference between the two. In all other cases, you come up with the numbers just like you did before. Now, I said that was the last example, and I meant it, but I want to talk about what would happen if you had a 4x4 system or higher. Suppose we had an augmented matrix A, B, C, D, Q, E, F, G, H, R, I, J, K, L, S, M, N, O, P, T. We would want zeros in strategically located places. We would want ones. The systematic way to do it, I'd say go for zeros in the first entries of the second, third, and fourth rows. Do those first. Then you'd go for zeros in the second entries of the third and fourth rows. Second. Then you would go for a 0 in the third entry of the fourth row. Do that third. And then you'd continue that pattern, the counterclockwise pattern that we were looking at before for the upper right triangular zeros. Start with the fourth column, and then the third column, and then the second column. And if you always do that counterclockwise approach to getting your zeros in the triangles, then things will go pretty well for you. There's no one step that's hard. It's just tedious, but it's doable. Once you have all your zeros, after that, then you go for your ones down the diagonal. Again, I don't care who tells you what. Just trust me on this one.